When you turn on a light, something very small begins a long trip. It leaves the lamp, crosses the room, and gently reaches your eyes. It happens so smoothly that it feels ordinary. But for a long time, scientists were confused by this simple thing. They thought light was like water waves spreading out smoothly everywhere. Then, strange things started to happen. Some metals refused to react to light unless the light was just the right kind. No matter how bright the light was, nothing happened until suddenly it did. It was as if light arrived in tiny steps instead of a smooth flow. In this story, we will slowly explore that mystery. We will see why light sometimes behaves like a wave and sometimes like little packets that arrive one by one. We won't rush. We'll follow what experiments quietly showed us. And by the end, you'll see why light is far more surprising than it looks and why the universe chose to work this way. If light creates color, why did the universe spend its earliest ages filled with light, yet entirely without color at all? To understand this, we have to set aside everything our eyes tell us about brightness, glow, and hue, and return to a time when the universe was young, dense, and unforgiving. In the first moments after the Big Bang, space was not empty, and it was not calm. It was a hot, expanding mixture of energy, elementary particles, and radiation. Photons were everywhere. In fact, they vastly outnumbered matter. Yet despite this ocean of light, the universe was visually dark. Not dim, not shadowed, colorless, in a more fundamental sense. This sounds contradictory because we instinctively link light and color as the same thing, but in physics, they are not. Light can exist without color ever becoming visible. Color requires permission from matter and space-time, and in the early universe, that permission had not yet been granted. In the first fraction of a second, after the Big Bang, temperatures were so high that no stable atoms could exist. Protons and electrons did not bind together. They collided constantly, separating as quickly as they met. Photons, which today can travel freely across billions of kilometers, were trapped in this dense plasma. Every attempt to move forward ended in a collision. A photon would travel a tiny distance, strike a charged particle, scatter, lose its direction, and begin again. The universe was filled with light, but light could not go anywhere. Modern measurements from NASA and ESA confirm this picture through precise observations of the cosmic microwave background. That radiation is not a glow from stars or galaxies. It is the fossil light, released when the universe finally changed its rules. But before that moment, for nearly 380000 years, photons were imprisoned by matter itself. This era is often described as opaque, but that word does not go far enough. Opaqueness today usually means light is absorbed or blocked. In the early universe, light was neither absorbed nor destroyed. It was constantly scattered. Every color was mixed with every other color before it could separate, stretch, or take form. Color needs contrast, structure, and freedom. None of those existed yet. As the universe expanded, it cooled. Expansion here is not an explosion into empty space, but the stretching of space itself. With cooling came a quiet but decisive transition. When the temperature dropped to about 3000 Kelvin, electrons slowed enough to bind with protons, forming neutral hydrogen atoms. This event is known as recombination. Though nothing was being recombined for the first time, this was the universe assembling atoms for the first time ever. The consequences were immediate and irreversible. Neutral atoms do not scatter light the way free charged particles do. Suddenly, photons could travel long distances without interruption. Space became transparent. Light decoupled from matter. The universe changed from an opaque plasma into a transparent cosmos, almost overnight on cosmic timescales. And yet, even at this moment, there was still no color in the way we understand it. The light released at recombination did have a characteristic spectrum. It was thermal radiation described with extraordinary accuracy by Planck's law. But as the universe expanded further, that light stretched. Wavelengths grew longer. Energies dropped. Over billions of years, what was once visible light cooled into microwave radiation. Today, it fills the universe at a temperature of 2.725 Kelvin. This is the cosmic microwave background, mapped in exquisite detail by satellites like COBE, WMAP, and Planck. This radiation is uniform to 1 part in 1,000,000. It does not carry reds, blues, or greens. It carries temperature variations, density fluctuations, and the imprint of the universe's earliest structure. It is light without color, because there were still no objects capable of selecting, absorbing, or responding differently to different wavelengths. Color does not live in light alone. Color emerges from interaction. This is one of the most important ideas in understanding photons. A photon does not carry redness or blueness as an intrinsic property. It carries energy and wavelength. Color only appears when matter responds unevenly to those wavelengths. Atoms must have allowed energy levels. Electrons must be bound. Surfaces must reflect some frequencies and absorb others. Eyes or detectors must translate wavelength differences into signals. None of that existed yet. For hundreds of millions of years after recombination, the universe entered what astronomers call the cosmic dark ages. This darkness was not caused by the absence of light, but by the absence of light sources that could structure that light. There were no stars, no galaxies, no heavy elements, only vast clouds of hydrogen and helium slowly drifting under gravity's influence. During this time, photons continued to travel, but they did not create images, shadows, or color. There were no surfaces to scatter light selectively, no atoms capable of producing emission lines, no chemical complexity. The universe was transparent but visually empty. The first stars changed everything. When gravity finally compressed regions of gas enough to ignite nuclear fusion, the universe gained its first structured light sources. Stars did not just emit light, they emitted light with specific spectra. Hydrogen absorbed and emitted at precise wavelengths. Later, heavier elements forged in stellar cores added complexity. Each element introduced new allowed transitions, new ways to interact with photons. This is where color truly began. Spectroscopy, the study of light divided by wavelength, shows us this history directly. When astronomers analyze light from distant stars and galaxies using instruments aboard the James Webb Space Telescope, they are not seeing color as decoration. They are reading atomic fingerprints. Each dark absorption line corresponds to a specific transition in an atom or molecule. Color becomes a record of physical conditions, temperature, density, composition, motion. This is why the early universe could be full of photons and yet empty of color. Photons alone are not enough. Color requires structure, rules, and selective interaction. As Carl Sagan once said, the cosmos is within us. We are made of star stuff. That statement is often quoted for its emotional resonance, but it has a precise physical meaning. The atoms that allow color to exist, carbon, oxygen, iron, did not exist in the early universe. They were manufactured inside stars, long after the first light had already crossed space. So when we ask why the early universe was dark, we are not asking why light was absent. We are asking why interaction was impossible. This distinction matters deeply for understanding what a photon is. A photon does not paint the universe by itself. It follows rules. It waits for matter to respond. It delivers energy only in ways the universe allows. In the early cosmos, the rules were too simple, the matter too uniform, the interactions too limited. Even today, this lesson remains visible. Interstellar space is filled with photons, yet it is mostly black. A beam of light crossing empty space does not reveal itself unless something interrupts it. Color appears only when light meets resistance, structure, or choice. The early universe had light everywhere, but nothing to stop it, shape it, or read it. If photons existed long before color, long before stars, long before observers, then what does a photon really represent? Is it an object moving through space? Or is it a bookkeeping rule that only becomes real at the moment of interaction? As the universe grew more complex, photons did not change. The rules governing them did not change. What changed was the stage on which they were allowed to act. And the next step in this story begins when experiments on Earth forced physicists to confront the same question but under laboratory lights that behaved very differently than the ancient sky. How can something with no size, no mass, and no place to stand still strike a piece of metal with the certainty of a solid hit? At the end of the 19th century, physics believed it had reached a comfortable understanding of light. Light was an electromagnetic wave. It spread continuously through space. It carried energy the same way waves on water carry motion smoothly, gradually, and without indivisible steps. Increase the brightness and you deliver more energy. Reduce it and you deliver less. Color, according to this picture, only changed how the wave oscillated, not how energy was handed over. This view was not naive. It was supported by Maxwell's equations, among the most successful mathematical descriptions ever written. They explained reflection, refraction, diffraction, radio transmission, and the behavior of electric and magnetic fields with astonishing accuracy. There was no sense that something essential was missing. Then metals began to misbehave. When physicists illuminated certain metal surfaces with light, electrons were sometimes ejected from the material. This phenomenon was not mysterious in itself. If energy strikes matter, matter can respond. What was shocking was how the response occurred. First, the timing. Electrons appeared instantly without delay. According to wave theory, a weak light source should take time to deliver enough energy to an electron. The way a gentle push repeated many times can eventually move an object. But even the faintest light of the right color caused electrons to emerge immediately. Second, the threshold. Below a certain frequency, no electrons were ejected at all. It did not matter how intense the light was. You could increase brightness indefinitely and still observe nothing. Above the threshold frequency, electrons appeared even when the light was extremely dim. Third, the energy. The speed of the ejected electrons depended on the color of the light, not on its brightness. Brighter light produced more electrons, but not faster ones. These three facts could not be reconciled with any wave-based picture of energy transfer. This was not a theoretical discomfort. It was an experimental refusal. Nature was not meeting physics halfway. It was insisting on a different rule. In 1905, Albert Einstein addressed this problem with unusual restraint. He did not attempt to save classical theory with complicated modifications. He accepted what the experiments were saying and followed them to their logical conclusion. Einstein proposed that when light interacts with matter, it does not deliver energy continuously. Instead, energy arrives in discrete units. Each unit carries an amount of energy proportional to the light's frequency. If that amount is sufficient to free an electron from a metal, the electron escapes. If it is not, nothing happens. There is no gradual accumulation. There is no partial transfer. The interaction either occurs or it does not. Einstein was careful not to describe these units as ordinary particles. His wording was deliberate. Light behaves as if it consists of energy quanta. This was not a philosophical claim about what light is. It was a statement about how energy exchange occurs. This distinction matters. If photons were simply tiny material bullets, they would possess properties like size, shape, and rest mass. They do not. If they were merely ripples in a field, electrons would respond gradually. They do not. The photon occupies a category that classical physics did not prepare us for. The photoelectric effect forces a precise conclusion. When light interacts with matter, the interaction is quantized. Energy is delivered in indivisible events. One way to see this clearly is to imagine a turnstile. No matter how gently you push, the turnstile rotates only in fixed steps. Pushing harder does not change the size of a step. It only increases how often the steps occur. In the photoelectric effect, brightness controls the number of interaction events per second. Frequency controls the energy per event. This explains why dim blue light works, while bright red light does not. Blue light carries higher energy quanta. Red light carries lower energy quanta. No amount of brightness can compensate for insufficient energy per quantum. From this perspective, the photon is not a thing moving through space. It is the smallest allowed transaction between electromagnetic fields and matter. This view becomes even clearer when experiments are refined to extreme limits. When light sources are attenuated so strongly that photons arrive one at a time, detectors still register discrete clicks. Each click corresponds to a full energy transfer. There are no half clicks. There are no smeared detections. Importantly, nothing in these experiments reveals a photon traveling through space like a miniature projectile. Between emission and detection theory does not describe a localized object. It describes a probability distribution. The particle-like behavior appears only at the moment of interaction. This is why modern quantum theory avoids asking where the photon is before it is detected. That question has no operational meaning. What can be predicted with extraordinary precision is the probability of where an interaction will occur. This distinction often causes confusion because the word particle carries intuitive baggage. We imagine small, solid objects moving along paths. Photons do not do that. They do not have trajectories in the classical sense. They do not slow down, speed up, or wait, yet when they interact, they do so all at once. This duality is not a compromise. It is a replacement. The universe does not choose between waves and particles. It uses a deeper rule that produces wave-like propagation and particle-like interaction as two limiting behaviors of the same underlying structure. The photoelectric effect was the first clear demonstration of this rule. Einstein's proposal was initially controversial even to those who accepted quantum ideas elsewhere. Max Planck, who had introduced quantization reluctantly in blackbody radiation, did not immediately accept photons as real entities. He viewed quantization as a mathematical device, not a physical statement about light itself. But experiments accumulated. Compton scattering showed that light exchanges momentum with electrons in discrete amounts. The angles and energies matched calculations that treated photons as carriers of momentum despite having no mass. Once again, the interaction occurred in indivisible steps. Radiation pressure confirmed the same conclusion. Light can exert force on mirrors not as a continuous push, but through momentum transfer events, whose total effect averages out to a measurable pressure. Each new experiment reinforced the same message. The universe does not allow electromagnetic energy to be transferred arbitrarily. There is a smallest unit of exchange. This is why describing photons as particles of light is both useful and misleading. It is useful because it captures the discreteness of interaction. It is misleading because it suggests a physical object with independent existence between interactions. A more accurate statement is this: a photon is defined by how electromagnetic energy is exchanged, not by how something travels through space. This perspective resolves several apparent paradoxes. It explains why photons have momentum without mass. Momentum belongs to energy flow, not to matter alone. It explains why photons have no rest frame. Rest is a property of objects that persist in time. Photons are defined by transitions between events. For physics, the same idea carries profound consequences. It means that reality at small scales is built from events, not from continuously evolving substances. The smoothness we experience at large scales emerges from enormous numbers of discrete interactions happening too quickly and too densely for us to notice individually. The photoelectric effect is often taught as a historical footnote. In truth, it marks a turning point in how physics understands interaction itself. It tells us that the universe enforces limits on how finely energy can be divided. Einstein received the Nobel Prize not for relativity but for explaining this effect. The reason was simple. The photoelectric effect was unambiguous. It was measurable. It forced a change in worldview based on data alone. And yet, this was only the beginning of the trouble. If photons behave like particles at the moment of interaction, what governs their behavior when they are not interacting? How does a single photon sent alone manage to produce patterns that look unmistakably like waves? That tension does not dissolve here. It sharpens. Because once physicists learned that light arrives in indivisible impacts, the next experiments showed something even harder to accept. Even when photons are sent one by one, they still build interference pattern structures that seem to require waves spreading through space. And that is where the next fracture in classical thinking becomes impossible to ignore. How can one indivisible event, arriving one at a time, slowly draw a pattern that seems to require many waves acting together? This question did not emerge from speculation. It came from a simple experiment that refused to behave simply. When light passes through two narrow openings and lands on a screen, it produces a pattern of bright and dark bands. This was well known in the 19th century. It was taken as strong evidence that light is a wave. Waves overlap. Where peaks meet peaks, the signal is strong. Where peaks meet troughs, the signal cancels. The mathematics works cleanly. The picture feels complete. Then physicists began to lower the light level. They reduced the intensity until photons were emitted one by one. Not a stream, not a pulse. Single, well-separated events. Each photon left the source alone, crossed the apparatus alone, and struck the detector alone. Nothing about the setup allowed photons to interact with one another. And yet, after many photons were recorded, the same interference pattern appeared. Not immediately. At first, the detector showed isolated dots. Each dot marked the arrival of one photon. There were no bands, no waves, no structure. But as the number of detected photons increased, a pattern slowly emerged. Bright regions grew brighter. Dark regions remained empty. Eventually, the familiar wave-like interference fringes became unmistakable. This was not an illusion. It has been reproduced countless times with photons, electrons, neutrons, and even larger molecules. The result does not depend on technology or interpretation. It depends only on the rules of quantum mechanics. The difficulty is not mathematical. The equations predict the pattern perfectly. The difficulty is conceptual. If a photon is an indivisible event, how can it produce an interference pattern that seems to require splitting, overlapping, and recombining? How does one event behave as if it has explored multiple paths? This is the point at which classical pictures fail completely. In classical physics, an object goes through one opening or the other. A wave goes through both. There is no third option. But the single photon experiment demands a third description. The photon is not a wave in space in the classical sense. It is not a particle following a definite path either. The key insight is this: the wave-like behavior does not belong to the photon as a thing. It belongs to the probability structure that governs where the photon can be detected. Between emission and detection, quantum theory does not describe a photon as occupying a single location. It describes a set of possible outcomes, each with a well-defined probability. These probabilities are not assigned independently. They are linked in a way that allows interference. When both slits are open, the probability distribution at the screen contains regions where outcomes reinforce and regions where they cancel. The photon does not split into pieces. The probability of detection does. Each individual detection is localized. One photon produces one dot, but the pattern formed by many dots reflects the underlying probability structure, not the behavior of individual particles as classical objects. This distinction is subtle, but it is central. The experiment does not show that a photon interferes with itself as a physical object. It shows that the rules assigning probabilities to detection outcomes allow interference. The wave is not something the photon is. It is something the theory uses to calculate what can happen. This is why attempts to imagine the photon physically dividing and recombining lead to confusion. There is no experimental evidence that a photon travels two paths simultaneously as a miniature object. What exists simultaneously are multiple allowed possibilities encoded mathematically. This is also why adding detectors at the slits changes the result. If you place a device to determine which slit the photon passes, through the interference pattern disappears. The probabilities reorganize. The experiment now assigns distinct outcomes to distinct paths. Without overlap in probability, there is no interference. Nothing mystical occurs. The experimental conditions change what can be predicted. The pattern responds accordingly. This is why Richard Feynman referred to the double-slit experiment as the heart of quantum mechanics. Not because it is mysterious, but because it exposes the limits of classical reasoning in the clearest possible way. No classical picture survives intact, and yet the experimental facts remain precise, repeatable, and calm. It is important to notice what does not happen. The photon does not gradually smear across the screen. It does not arrive half here and half there. Each detection is sharp. Each interaction is complete. The discreteness observed in the photoelectric effect remains intact. The wave-like aspect appears only in the distribution of many such events. This dual structure is not a contradiction. It is a layered description. At the level of individual interactions, nature behaves in discrete steps. At the level of statistical patterns, those steps arrange themselves according to wave-like rules. This idea becomes clearer when experiments are slowed down even further. In modern laboratories, photons are sent through double-slit setups, with delays long enough that only one photon exists in the apparatus at any time. The apparatus remains stable. The environment is controlled. Nothing carries memory from one photon to the next. And still the pattern builds. The conclusion is unavoidable. The interference does not arise from interactions between photons. It arises from the structure of the probability distribution governing each photon individually. Each photon chooses one place to land, but the rules that guide those choices are shaped by the whole setup. Over time, the choices make a picture. It applies to all quantum objects. Electrons, atoms, even complex molecules display the same behavior when isolated and allowed to interfere. The double-slit experiment forces us to separate two ideas that classical physics treated as inseparable. The path an object takes and the outcome of a measurement are no longer the same thing. Quantum theory predicts outcomes, not trajectories. This does not mean that anything is allowed. The probabilities are calculated precisely. They depend on distances, wavelengths, slit widths, and geometry. Change the spacing of the slits, and the pattern changes. Change the wavelength of the photon, and the spacing of the fringes changes accordingly. Nothing here is vague. What disappears is the idea that particles must always follow well-defined paths in space. That idea is not wrong at large scales. It is simply not fundamental. This is why the photon cannot be fully described as a particle or as a wave. Those are classical categories. The photon obeys rules that reduce to particle-like behavior in interactions and wave-like behavior in probability distributions. The mathematics that encodes this behavior uses wave equations, but those waves do not represent physical ripples in space. They represent amplitudes whose squares give probabilities. Interference arises when these amplitudes combine, not when physical objects overlap. This distinction explains why no experiment has ever observed a photon half absorbed or partially detected. Detection is always complete. What interferes is not the photon but the information about where it might be detected. The historical significance of this realization cannot be overstated. Early physicists resisted it precisely because it demanded a new way of thinking. Even Einstein, who introduced photons, was uncomfortable with the probabilistic interpretation that later emerged. But the experiments left no room for alternatives. Over decades, refinements of the double-slit experiment confirmed the same conclusion with increasing clarity. Interference patterns persist, even when environmental noise is minimized. They vanish when which path information becomes available, even in principle. The universe responds not to what is observed, but to what can be known. This is not philosophy. It is operational fact. The rules governing photons are not concerned with human awareness. They are concerned with physical interaction. If the experimental setup allows different paths to be distinguished, the probabilities reorganize. If it does not, they interfere. The photon does not decide. The setup decides. This insight connects directly to the previous part. Photons behave like particles at the moment of interaction because interactions are quantized. They behave like waves in their distribution because probabilities propagate according to wave equations. Both behaviors are correct. Neither is complete alone. And this prepares the ground for the next step, which deepens the tension rather than resolving it. Because if interference belongs to probability, not to the photon as an object, then what determines how much energy is delivered in each interaction, and why that energy depends only on frequency? That question does not introduce a new phenomenon. It sharpens one already in view, waiting to be examined from a different angle. Why can a very faint light knock electrons out of metal, while a much brighter light sometimes cannot, no matter how long you wait? This question sounds simple, almost unfairly simple, because it seems to violate everyday experience. If you push harder, things move more. If you add more water, a cup fills faster. If you turn up the volume, the sound becomes stronger. For centuries, physics assumed light followed the same logic. Brighter light should deliver more energy. Dimmer light should deliver less. Color in this view was only decoration. Experiments disagreed. When physicists studied how light interacts with matter, especially with atoms and electrons, they found a rule that refused to bend. The energy delivered by light did not depend on how bright it was. It depended only on its frequency. Brightness controlled how many photons arrived. Frequency controlled how much energy each photon carried. These two roles could not be exchanged. This was not an abstract idea. It emerged from precise measurements and stubborn failures of classical explanations. In the photoelectric effect, electrons are ejected from a metal surface only if the incoming light has a frequency above a specific threshold. Below that threshold, nothing happens. Increasing brightness does not help. Above the threshold, even extremely weak light causes immediate ejection. The electrons do not wait. They do not accumulate energy gradually. They respond to a single interaction. This behavior forces a clear conclusion. Light does not deliver energy smoothly. It delivers energy in fixed portions. Each portion has an amount of energy determined entirely by frequency. This idea was deeply uncomfortable when it was first proposed. Classical wave theory had no place for it. In wave theory, intensity measures energy flow. Frequency measures oscillation rate. There is no reason one should control the other, but nature insisted. The relationship between photon energy and frequency was first recognized in the context of blackbody radiation. Max Planck found that heated objects emit light in a way that could only be explained if energy exchange occurred in discrete amounts proportional to frequency. At the time, Planck treated this as a mathematical trick, not a statement about reality. Einstein went further. He applied the same idea directly to light itself. If energy exchange is quantized, then each quantum of light must carry a specific energy. That energy depends only on frequency, not on brightness, not on distance. not on time. This single rule explains an enormous range of phenomena. It explains why ultraviolet light can damage DNA, while visible red light cannot. Ultraviolet photons carry more energy per photon. They can break chemical bonds. Red photons cannot, regardless of how many arrive per second. Increasing intensity increases the number of interactions, not the strength of each interaction. It explains why X-rays penetrate soft tissue, but are absorbed by bone. X-ray photons carry far more energy per photon than visible light. The difference is not subtle, it is structural. It explains why atomic spectra consist of sharp lines rather than continuous smears. Atoms absorb and emit light only at specific frequencies, because electrons in atoms can change energy only in specific steps. When an electron moves between allowed energy levels, the photon involved must carry exactly the right amount of energy. No more, no less. This is where frequency becomes the language of energy exchange. Atoms do not respond to brightness the way macroscopic objects do. They respond to resonance. They respond to matching conditions. Either the photon carries the right energy to drive a transition, or it does not. There is no gradual negotiation. Spectroscopy grew directly from this insight. When scientists analyze light from stars and galaxies, they do not measure brightness alone. They measure frequency distributions. Each absorption line reveals a specific atomic transition. Each emission line reveals a specific energy difference inside atoms. This is why light carries information so efficiently. Frequency encodes structure. Intensity encodes quantity. Space-based observatories, operated by NASA and ESA, rely on this principle constantly. Instruments aboard the James Webb Space Telescope measure infrared frequencies to determine the chemical composition, temperature, and motion of distant objects. They do not see color as decoration. They read frequency as physics. The rule that energy depends only on frequency is not arbitrary. It is tied to the structure of quantum systems themselves. Inside atoms, electrons are bound by electromagnetic forces. These forces allow only certain stable configurations. Each configuration has a specific energy. Transitions between them require precise energy changes. Light serves as the messenger that carries those changes. If photon energy depended on intensity, atoms would behave chaotically. They would absorb energy, gradually blur transitions, and lose stability. The universe would not support chemistry as we know it. Instead, energy exchange is quantized. Frequency sets the size of each step. Intensity sets how often steps occur. Light comes in steps. Some steps are small, some steps are big. Taking many small steps does not equal one big step. You cannot climb a tall stair by taking many tiny ones at once. This idea feels counterintuitive because we rarely encounter individual photons in daily life. At human scales, enormous numbers of photons arrive together. Their discrete nature averages out. Light appears smooth. But when experiments isolate individual interactions, the stepping becomes visible. The language physicists use to express this rule is compact, but the meaning is straightforward. Higher frequency means higher energy per photon. Lower frequency means lower energy per photon. Brightness controls how many photons arrive per second. This separation is absolute. No experiment has ever violated it. Richard Feynman summarized this with characteristic clarity. Light comes in chunks. He did not mean chunks as tiny balls. He meant chunks of interaction, fixed units of energy exchange. This rule also explains why intensity can be misleading. A bright infrared lamp may feel warm because many low-energy photons arrive each second, transferring energy collectively. But no single infrared photon can break a chemical bond the way an ultraviolet photon can. The effect depends on accumulation, not individual impact. This distinction matters enormously in biology, chemistry, and astronomy. In photosynthesis, for example, chlorophyll absorbs photons at specific frequencies. Those frequencies match energy gaps within the molecule. Light outside that range is largely ignored. The plant does not become more efficient simply because the light is brighter. It becomes efficient when the frequencies match. In astronomy, frequency tells us about temperature. Hot objects emit higher frequency photons on average. Cooler objects emit lower frequency photons. Brightness alone cannot distinguish a small hot object from a large cool one. Frequency distribution can. This is why early confusion about light delayed understanding for so long. Classical physics treated energy flow as continuous. Quantum physics revealed that energy exchange is digital in character. Nature counts. Once this rule is accepted, many puzzles dissolve. The photoelectric effect becomes natural. Atomic spectra become inevitable. Molecular stability becomes understandable. Even the limits of vision make sense. Human eyes respond only to a narrow band of frequencies because retinal molecules are tuned to specific energy steps. Nothing about this picture is mystical. It is constrained by measurement. Every claim is anchored in reproducible experiments. The rule also prepares us for something deeper. If photon energy depends only on frequency, then color is not an aesthetic feature. It is a measure of energy. Different colors correspond to different capacities to drive physical change. This redefines how we think about light entirely. Light is not a substance filling space. It is a structured carrier of energy, constrained by the rules of quantum interaction. And this brings us to the edge of the next difficulty. If energy is exchanged in fixed units, and those units are determined by frequency, then photons must carry momentum as well. Energy flow and momentum flow are inseparable in physics. But photons have no mass. How can something without mass push on mirrors, transfer recoil to electrons, and bend around galaxies under gravity? That question does not contradict what we have learned. It sharpens it. How can something with no weight, no rest, mass, and no substance still push on mirrors, knock electrons backward, and curve its path around entire galaxies? At first glance, this sounds like a contradiction built into nature. Momentum in everyday life belongs to things with mass. A moving ball has momentum. A rolling stone has momentum. If something is weightless, how could it possibly push anything at all? And yet light does. This is not a theoretical curiosity. It is a measured fact, confirmed repeatedly in laboratories and across the universe. Light pushes on matter. Light transfers recoil. Light changes direction in gravitational fields. These effects are not small. They are precise, predictable, and unavoidable. The puzzle only exists because classical intuition tied momentum too tightly to mass. In classical mechanics, momentum is defined as mass multiplied by velocity. Remove mass and momentum seems to vanish. But this definition was never meant to be universal. It works well for slow, massive objects. It breaks down when energy itself becomes the carrier of motion. Light forced physics to confront that limit. Long before relativity experiments already hinted that light carries momentum. In the early 20th century, physicists measured radiation pressure, the tiny force exerted by light when it strikes a surface. The effect is subtle, but it is real. When light reflects off a mirror, it transfers momentum to that mirror. The mirror recoils ever so slightly. This recoil cannot be explained if light carries energy but no momentum. The measurements leave no ambiguity. Light exerts pressure because it carries momentum. This pressure is not a metaphor. It has been measured, quantified, and put to use. Modern concepts like solar sails rely on it. A spacecraft equipped with a large, reflective surface can gain momentum simply by reflecting sunlight. No fuel is expelled. No mass is thrown backward. Momentum is transferred directly from photons. This already tells us something essential. Momentum does not belong exclusively to mass. It belongs to energy in motion. The next decisive confirmation came from Compton scattering. When high-energy light collides with electrons, the outgoing light has a longer wavelength than the incoming light, and the electron recoils. The change in wavelength matches exactly what is required if the photon transfers both energy and momentum to the electron. There is no room for interpretation here. The numbers work only if photons carry momentum proportional to their energy. At this point, physics faced a choice: either abandon conservation laws that had never failed before, or accept that momentum exists without mass. Relativity made that choice unavoidable. In special relativity, mass and energy are not separate substances. They are related aspects of the same physical quantity. Energy has inertia. Energy resists acceleration. Energy carries momentum when it moves. For objects with mass, momentum depends on both mass and velocity. For light, which always moves at the same speed in vacuum, momentum depends entirely on energy. This is not an added rule. It is a consequence of how space-time itself is structured. In relativity, the speed of light is not just the speed at which light travels. It is the maximum speed at which any influence can propagate. Photons always move at this speed, not because they are special objects, but because they have no rest frame. There is no state in which a photon is stationary. As a result, photons cannot store energy as mass. All their energy is kinetic in nature, and moving energy carries momentum. This reframes the original question. The mystery is not why photons have momentum without mass. The mystery is why we ever thought momentum required mass in the first place. Once this is understood, several phenomena that once seemed unrelated snap into alignment. Radiation pressure becomes inevitable. Compton scattering becomes inevitable. Momentum transfer in atomic interactions becomes inevitable. And then, gravity enters the picture. According to general relativity, gravity is not a force that pulls on mass. It is the curvature of space-time caused by energy and momentum. Everything that moves through space-time follows the geometry of that curvature. Light follows it too. This is why light bends around massive objects, not because gravity pulls on photons as if they were tiny stones, but because space-time itself is curved. Photons move along the straightest possible paths in curved space-time, which appear bent when viewed from afar. This effect was first confirmed during a solar eclipse in 1919, when starlight passing near the Sun was observed to shift its apparent position. The amount of bending matched Einstein's predictions precisely. Since then, gravitational lensing has become one of the most powerful tools in astronomy. Galaxies bend light from objects behind them, creating arcs, rings, and multiple images. These distortions allow astronomers to map the distribution of mass, including invisible dark matter. Observatories operated by NASA and ESA rely on this effect routinely. The James Webb Space Telescope observes distant galaxies whose light has traveled billions of years, bent and redirected by massive structures along the way. Throughout this journey, the photons never slow down. Their speed remains constant. What changes is their direction. This alone tells us something profound. Gravity affects motion without changing energy in the usual sense. It reshapes paths rather than draining speed. This behavior would be impossible if photons behaved like classical particles with mass. They would accelerate, decelerate, and accumulate potential energy. Instead, photons respond only to geometry. Momentum in this context is not a measure of weight. It is a measure of how energy moves through space-time. Light can push, even though it is very light, because pushing does not require heaviness. It requires motion. Light is always moving, and moving things can push. It means that mass is not the fundamental carrier of motion. Energy is. This insight unifies phenomena across scales. From photons bouncing off mirrors in laboratories to light bending around clusters of galaxies, the same rule applies. Energy flow carries momentum. Space-time responds to it. This also explains why photons contribute to gravity. Although photons have no rest mass, they carry energy and momentum, and therefore they influence space-time curvature. In extreme environments such as the early universe or near black holes, radiation itself plays a significant gravitational role. The early universe was dominated by radiation. Photons controlled its expansion rate. Matter came later. Gravity responded to energy first, mass second. This overturns everyday intuition, but it matches observation precisely. The idea that light has momentum without mass is not a loophole or exception. It is a demonstration that our classical categories were incomplete. Mass is one way to store energy. Motion is another. Both curve space-time. Both carry momentum. Once this is accepted, the photon becomes easier to understand. It is not a tiny object that somehow cheats the rules. It is a clean example of how the rules actually work. A photon is a packet of energy that moves at the universal speed limit. Because it moves, it carries momentum. Because space-time responds to energy and momentum, photons bend in gravitational fields. Because interactions are quantized, momentum transfer occurs in discrete steps. Nothing about this picture is inconsistent. It is only unfamiliar. And now, with momentum accounted for, another question becomes unavoidable. If photons always move at the same speed regardless of their energy, and if they carry momentum without mass, then what fixes that speed in the first place? Why is the speed of light not a property of light but a property of space-time itself? That question does not introduce a new topic. It sharpens everything we have already learned. Why is the speed of light not something light decides, but something the universe itself enforces? At first, this sounds like a strange way to ask the question. In everyday life, speed belongs to objects. A car can move slowly or quickly. A ball can be thrown gently or hard. We expect speed to depend on effort, on conditions, on choice. It feels natural to imagine light behaving the same way, perhaps slowing down when it is weak or speeding up when it is strong. But light does nothing of the sort. Every photon in empty space moves at exactly the same speed. Not almost the same, not on average, exactly the same. Photons emitted from a candle, a laser, or a distant galaxy all travel through vacuum at one fixed speed, regardless of their energy, color, or origin. This fact is not a coincidence. It is not a property of photons as objects. It is a property of space-time itself. To see why, we need to step away from the idea that light is something moving through space, and instead understand that light reveals how space and time are stitched together. Before the 20th century, physicists believed that space and time were absolute. Space was a static stage. Time flowed uniformly everywhere. Speeds were measured relative to this fixed background. Light in this picture should have behaved like sound or water waves, moving faster or slower depending on conditions. Experiments did not agree. Repeated measurements showed that the speed of light in vacuum is the same for all observers, regardless of how they move. This result was deeply unsettling. It meant that something was wrong with the assumptions, not with the experiments. Albert Einstein took this seriously. He did not try to explain why light moves at a particular speed by appealing to its nature. Instead, he reversed the logic. He treated the speed of light as a fundamental feature of reality, and asked what space and time must be like for that to be true. The answer reshaped physics. In special relativity, space and time are not separate ingredients. They are woven together into space-time. Distances and durations are not absolute. They depend on how observers move relative to one another. What remains fixed is not space, not time, but the maximum speed at which information and causation can travel. That speed is what we call the speed of light. In this framework, photons do not choose to move at that speed. They must. There is no alternative available to them. This is because photons have no rest frame. There is no way to move alongside a photon and see it at rest. If you try to imagine slowing down to match a photon's speed, the rules of space-time prevent you from ever reaching that state. Time and distance adjust in such a way that the speed of light remains unchanged. This is not a technical trick. It is a direct consequence of how space-time measures intervals. For objects with mass, space-time allows a range of speeds. These objects can slow down, stop, accelerate, and rest. Their motion through space and time can trade off. Move faster through space, and you move slower through time. This is time dilation, and it has been measured precisely using atomic clocks. Photons are different. They move through space-time in such a way that all of their motion is spatial. None of it is temporal. Along a photon's path, time does not advance. This is not poetry. It is a precise statement derived from the geometry of space-time. This is why saying that time has no meaning along a photon's path is not a metaphor. It is a mathematical result. There is no proper time associated with a photon's journey. From emission to absorption, the space-time interval is zero. This explains why photons cannot slow down or speed up in vacuum. There is no internal clock that could tick faster or slower. There is no rest energy to convert into kinetic energy. The photon's motion is fixed by the structure of space-time itself. When light travels through materials, it appears to slow down, but this is not because photons are moving more slowly between atoms. It is because photons interact with matter being absorbed and re-emitted, delayed by the response of electrons. In the empty vacuum between atoms, photons always move at the same speed. Space sets the limit. Light reveals it. This idea has been confirmed in countless experiments. From precise laboratory measurements to astronomical observations spanning billions of years, no deviation has ever been found. High-energy photons and low-energy photons arrive together from distant cosmic events. Gamma rays and radio waves, emitted simultaneously from faraway galaxies, reach Earth at the same time, within extremely tight limits. Observations supported by organizations such as NASA and ESA rely on this invariance constantly. The timing of signals, the reconstruction of distant explosions, and the mapping of space-time itself all depend on the fact that light's speed is fixed. The James Webb Space Telescope, for example, observes light that has traveled for billions of years. That light has crossed expanding space, passed through gravitational fields, and been stretched to longer wavelengths. Yet at every moment in the local vacuum it moved at the same speed. This invariance is what allows causality to exist. If signals could propagate faster than light, cause and effect would lose their order. Events could influence their own past. Physics would no longer be able to define what it means for one event to happen before another. The fixed speed of light protects the logical structure of reality. From this perspective, the photon is not special because it is light. It is special because it moves at the speed that defines space-time itself. This also explains why photons have momentum without mass, as we explored earlier. Momentum belongs to energy in motion. Since photons always move at the maximum allowed speed, their energy is entirely associated with motion through space, not with rest. Light always runs as fast as the universe allows. There is no faster road and no slower one when nothing gets in the way. It means that speed is not relative in the way we once imagined. Time adjusts, space adjusts, speed does not. This is why all observers, no matter how they move, measure the same speed of light in vacuum. Their rulers and clocks change not the light. Einstein once summarized this shift by noting that the laws of physics must look the same to all observers. The speed of light is the anchor that makes that possible. This also clarifies why photons cannot age. Aging requires time. Time requires a rest frame. Photons have none. From the photon's perspective, emission and absorption are not separated by a duration. They are connected directly. This does not mean that photons experience the universe. It means that the concept of experience does not apply. The fixed speed of light is not a detail added onto physics. It is the backbone of modern space-time theory. It determines how distances and times relate. It determines how energy and momentum transform. It determines how gravity curves paths without changing speeds. Once this is understood, the question shifts again. If photons are not objects moving through space in the usual sense, but manifestations of space-time structure responding to electromagnetic energy, then what exactly is a photon in the deeper description of nature? That question does not overturn what we have learned so far. It completes it by forcing us to move one level deeper into the language of fields rather than particles. What if a photon is not something moving through space at all, but space itself responding in the smallest way it is allowed to? By the time physics reached this question, the old picture of light as a tiny object in motion was already under strain. We had seen that photons deliver energy in indivisible steps. We had seen that they interfere through probability, not through physical overlap. We had seen that they carry momentum without mass, and that they move at a speed fixed by space-time itself. Each of these facts could be explained on its own, but together they pointed toward a deeper description, one that no longer treated photons as independent little travelers crossing an empty stage. That description is quantum field theory. In this framework, the universe is not built from particles first with fields added later. It is built from fields everywhere, all the time. Every point in space carries properties that can respond, fluctuate, and interact. The electromagnetic field is one of these. It exists even when there is no light shining, just as the ocean exists even when its surface is calm. A photon in this view is not a thing flying through the field. It is the smallest possible excitation of the field itself. This change of perspective removes many puzzles at once. If photons were tiny objects, we would expect to track their paths, locate them precisely between interactions, and imagine them carrying properties like position and shape. Experiments never allow this. What experiments do allow is counting how much energy is exchanged, how often interactions occur, and how probabilities evolve. Quantum field theory matches exactly what experiments demand, and nothing more. To understand why this matters, consider how classical descriptions work. When light is intense, such as sunlight or a laser beam, we describe it successfully as a wave. The electromagnetic field oscillates smoothly. The equations predict reflection, refraction, diffraction, and interference with extraordinary accuracy. No photon counting is needed. The field description alone works. But when light is weak, when interactions happen one by one, the wave description becomes insufficient. Detectors do not respond smoothly. They click. Energy arrives in discrete units. Counting becomes essential. These are not two different kinds of light. They are two limits of the same theory. Quantum field theory explains why. The electromagnetic field can exist in different states. Some states involve enormous numbers of excitations packed closely together. In those cases, the field behaves like a classical wave. Other states involve only a few excitations, or even just one. In those cases, the discrete nature of the field becomes unavoidable. The photon is the name we give to a single quantum of excitation in the electromagnetic field. This is not a metaphor. It is a precise statement about how the field stores and transfers energy. When an atom emits light, it does not throw a particle outward like a projectile. The atom changes its internal state, and the electromagnetic field adjusts accordingly. That adjustment propagates outward at the speed set by space-time. When another atom absorbs light, the field and the atom exchange energy again. The photon is not something in between. It is the bookkeeping of that exchange. This view explains why photons are defined by interaction, not by persistence. Between emission and absorption, the theory does not require a localized object. It requires only a consistent evolution of the field's state. This is also why the idea of a photon's position becomes fuzzy between interactions. Fields are extended by nature. They are defined everywhere. Asking where a photon is before it is detected is like asking where a ripple is before it reaches the shore. The ripple is not an object. It is a pattern in the field. Quantum field theory makes this precise by assigning probabilities to possible interactions, not trajectories to objects. Historically, this shift did not happen overnight. Early quantum mechanics treated particles and waves as separate entities, joined awkwardly by duality. Over time, it became clear that this language was provisional. A deeper structure was needed. That structure emerged in the middle of the 20th century, when physicists learned how to combine quantum principles with special relativity. The result was a theory in which fields, not particles, are fundamental. In this theory, every type of particle corresponds to a field. Electrons are excitations of the electron field. Quarks are excitations of quark fields. Photons are excitations of the electromagnetic field. This symmetry is not aesthetic. It is required for consistency. Relativity demands that no signal propagate faster than light. Quantum mechanics demands that interactions occur probabilistically. Fields allow both requirements to be satisfied simultaneously. Particle pictures alone do not. This field-based view also explains why photons can be created and destroyed. Particles in classical thinking persist unless something breaks them apart. Photons appear and disappear constantly. They are emitted, absorbed, scattered, and converted into matter under the right conditions. In field language, this is natural. Fields change state. Excitations come and go. This is why it makes sense to say that empty space is not truly empty. The electromagnetic field exists everywhere, even in its lowest energy state. That state is not a featureless void. It has structure fluctuations and rules. When a photon is present, the field is excited in a specific way. When it is not, the field remains in its ground state. This perspective also clarifies why classical wave descriptions work so well in everyday situations. When trillions upon trillions of photons are involved, individual excitations blur together. The field behaves smoothly. Counting becomes unnecessary. The classical equations emerge as an average description. This is not approximation in the sloppy sense. It is a precise limit. The same underlying theory produces both behaviors, depending on scale. Light is not little balls flying around. Light is space doing something. Sometimes space does it a lot, and it looks smooth. Sometimes space does it just a little, and it happens one step at a time. For physics, the same idea resolves contradictions that once seemed fundamental. It explains why interference patterns arise from probabilities rather than from splitting particles. It explains why photons have no size. It explains why they have no rest frame. It explains why energy and momentum are transferred discretely, even though fields are continuous. It also explains why different descriptions are useful in different contexts. Engineers designing lenses use classical waves. Astronomers counting faint signals from distant galaxies use photons. Both are correct. Neither is complete alone. Observatories, operated by organizations such as NASA, rely on this dual usefulness constantly. Instruments aboard space telescopes treat light as a wave when forming images and as photons when measuring faint spectra. The same electromagnetic field supports both tasks. Quantum field theory does not replace earlier physics. It contains it. This view also avoids unnecessary imagery. There is no need to imagine photons squeezing through slits bouncing like marbles or splitting and recombining. The field evolves. Probabilities interfere. Interactions occur. The language may feel abstract, but it matches what experiments demand, and nothing more. Perhaps the most important consequence of this shift is conceptual. It tells us that particles are not the building blocks of reality in the way we once thought. Fields are. Particles are how fields announce themselves when energy is exchanged. This is why the photon is not a thing you can point to between events. It is the smallest possible announcement the electromagnetic field can make. This also prepares us for what comes next. If photons are excitations of a field, and if fields carry structure beyond simple oscillation, then photons may carry more information than just energy and momentum. They may carry orientation, internal structure, and constraints that are invisible in classical descriptions. That possibility does not introduce a new mystery. It reveals one that has been present all along, waiting for the right language to describe it. How can light carry orientation, direction, and information when it has no solid body, no surface, and no physical axis to point along? At first glance, polarization seems like a technical detail, something added to light after its more important properties have already been explained. We learn that light has energy, that it travels at a fixed speed, that it can behave like waves or particles. Polarization often appears later, almost as an afterthought, and yet polarization turns out to be one of the clearest windows into the quantum structure of reality. To understand why, we need to start with something very simple. Light is an electromagnetic phenomenon. Even in classical physics, it is described as oscillations of electric and magnetic fields. These oscillations do not happen randomly. They occur in directions perpendicular to the direction of travel. That perpendicular orientation is what polarization refers to. In everyday light, such as sunlight or a lamp, these oscillations are mixed. They point in many directions at once. But when light is prepared in a controlled way, those oscillations can be aligned. They can have a definite orientation. At the classical level, this sounds straightforward. A wave can wiggle up and down, left and right, or in any combination. Polarization is simply the direction of that wiggle. Quantum physics changes the meaning entirely. When light is reduced to the level of single photons, polarization no longer describes a smooth oscillation in space. It becomes a discrete property of interaction. Each photon carries polarization as an internal degree of freedom. It is not something spread out along a wave. It is something revealed only when the photon interacts with matter. This is where polarization stops being geometry and becomes structure. A single photon can be prepared in a definite polarization state. When it encounters a polarizer, it does not partially pass through. It is either detected or not detected. The outcome is discrete. Yet when many photons are sent through the same setup, the statistics reproduce the smooth behavior predicted by wave theory. This dual behavior mirrors everything we have learned so far. Individual events are sharp. Patterns emerge only in collections. What makes polarization special is that it provides a clean, controllable two-state system. A photon can be polarized in one direction or an orthogonal direction. This makes it a natural testing ground for quantum logic. In quantum terms, polarization states form a simple space of possibilities. A photon can be prepared in one orientation or another, or in a superposition of both. This is not a statement about ignorance. It is a statement about how probabilities are structured. When a photon in a superposition of polarization states encounters a polarizer, the measurement does not reveal a pre-existing answer. It produces an outcome according to the rules of quantum probability. Change the orientation of the polarizer, and the statistics change accordingly. This is not a failure of realism. It is a feature of how information is encoded. Experiments with polarization were among the earliest to show how measurement shapes outcomes. When a photon passes through one polarizer and then another oriented differently, the result depends critically on the sequence and orientation of those measurements. Insert a third polarizer between two crossed ones, and photons reappear, where classical intuition predicts none. This behavior is not mysterious once the rules are understood. The first polarizer prepares the photon in a new state. The second measurement probes a different aspect of that state. The probabilities reorganize. Polarization shows us that quantum states are not lists of properties waiting to be revealed. They are instructions for how outcomes will be distributed under different measurements. This is why polarization became central to the development of quantum mechanics. It provided a simple, visualizable system in which abstract principles could be tested experimentally with extreme precision. Richard Feynman once remarked that quantum mechanics is not strange because it is complicated, but because it does not match how we expect the world to work. Polarization experiments make this mismatch visible without requiring complex mathematics. At the same time, polarization reveals something deeply physical. Photons possess a property called spin. This is not spin in the sense of a tiny object rotating. It is an intrinsic form of angular momentum. For photons, spin is tied directly to polarization. The allowed polarization states correspond to specific spin orientations relative to the direction of motion. This connection explains why photons have only two independent polarization states. Unlike massive particles, photons are constrained by their lack of rest frame. Their spin must align with their direction of motion. This alignment is called helicity. Helicity is not an abstract label. It has measurable consequences. It affects how photons interact with matter, how they are absorbed and emitted by atoms, and how they propagate through certain materials. In astrophysics, polarization carries information across vast distances. Light scattered by dust becomes polarized. Light emitted in strong magnetic fields acquires characteristic polarization signatures. By measuring polarization, astronomers can infer the geometry of distant environments that cannot be imaged directly. Instruments developed and operated by organizations such as NASA and ESA routinely measure polarization to study cosmic magnetic fields, interstellar dust, and the early universe. Polarization of the cosmic microwave background, for example, encodes information about primordial density fluctuations and gravitational waves from the universe's earliest moments. None of this would be possible if polarization were merely a classical orientation. At the quantum level, polarization behaves like a language with strict grammar. You cannot ask all questions at once. Measuring polarization along one axis limits what can be known about polarization along another. This is not because the photon hides information. It is because the information does not exist in that form until the measurement is made. This idea becomes especially clear in experiments involving entangled photons. When two photons are produced together in certain processes, their polarization states become linked. Measure one and the statistics of the other are immediately constrained no matter how far apart they are. These experiments do not transmit signals faster than light. They reveal correlations that were built into the joint quantum state from the beginning. Polarization provides a clean way to demonstrate this because the outcomes are binary and the predictions are exact. Once again, polarization shows us that quantum mechanics is not about particles carrying hidden instructions. It is about structured probabilities that govern interactions. Light can wiggle in different ways. When you put a special filter in front, light either matches the filter or it doesn't. It is not half-matching. It either works or it doesn't. But if you change the filter, the chances change. Polarization becomes a resource. It can encode information. It can be manipulated. It can be measured with precision. This is why photons are used in quantum communication and cryptography. Their polarization states can represent information in a way that reveals interference or eavesdropping immediately. The deeper lesson is this: polarization is not an extra property added to photons. It is a manifestation of the internal structure of quantum fields. It reflects constraints imposed by symmetry, relativity, and the nature of interaction itself. The electromagnetic field does not just oscillate, it carries orientation. That orientation is quantized. When the field interacts in its smallest units, that quantization becomes visible as photon polarization. This brings together everything we have learned so far. Photons are excitations of a field. Their energy depends on frequency. Their momentum belongs to energy flow. Their speed is set by spacetime. Their polarization reveals internal quantum structure. None of these features can be removed without breaking the theory. Each one reinforces the others. And now, with polarization understood as a quantum degree of freedom rather than a classical direction, another possibility comes into view. If photons carry energy, momentum, and polarization, and if these properties are governed by the same field-based rules, then photons are not fundamentally different from matter. Under the right conditions, energy and fields may reorganize themselves in ways that blur the boundary entirely. That transition does not require speculation. It has been observed. Why is mass sometimes nothing more than light caught in the right arrangement? At first, this sounds like a poetic idea, but it is not. It is a direct consequence of how energy and matter behave when the universe is pushed to its limits. In laboratories, in cosmic rays, and in the most extreme environments of space, light becomes matter, and matter becomes light again. This is not metaphor, it is measurement. For most of human history, matter and light seemed fundamentally different. Matter had weight. It stayed in place. It could be touched. Light had no weight. It moved too fast to catch. The two belonged to separate categories of reality. Modern physics erased that boundary. The bridge between them is energy. When Einstein introduced the idea that mass and energy are equivalent, it was not a statement about explosions or power generation. It was a statement about identity. Mass is a form of energy. Energy can take the form of mass. Under the right conditions, one becomes the other. Photons make this visible. A photon normally carries energy without mass. It moves at the maximum speed allowed by spacetime. But if a photon carries enough energy, and if it encounters the right environment, it can transform. It can become a pair of particles, an electron and its antimatter partner, a positron. This process is called pair production. It does not happen in empty space. Conservation laws forbid a single photon from turning into matter without something nearby to absorb momentum. Usually that something is a nucleus or another particle. The environment matters. When the conditions are right, the photon disappears. In its place appear two particles with mass. Their combined mass equals the energy the photon carried, adjusted precisely according to the rules of relativity. No energy is lost. No mass appears from nowhere. The bookkeeping is exact. This was not discovered by accident. It was predicted by relativistic quantum theory and confirmed experimentally in the early 20th century. Later, particle accelerators made the process routine. High-energy photons are produced, guided, and converted into matter under controlled conditions. The reverse process is just as revealing. When an electron meets a positron, they do not collide like billiard balls and bounce away. They annihilate. Their mass disappears. In its place appear photons, usually two or more, carrying away exactly the energy and momentum the particles once embodied. This is not destruction. It is transformation. Matter becomes light. Light becomes matter. The boundary dissolves. This symmetry is not optional. It is required by the internal consistency of the theory. If energy and mass are equivalent, then any process that creates one must allow the reverse. Nature respects that balance. What makes photons central to this story is that they are the simplest carriers of energy. They have no rest mass, no charge, and no internal structure beyond what we have already explored. When they convert into matter, they reveal how little is required to build mass. Mass is not a substance added on top of energy. It is energy organized in a way that resists acceleration. When energy is trapped, confined, or bound into stable configurations, it acquires mass. Electrons and positrons are stable excitations of quantum fields. They persist. They can slow down. They can rest. That persistence is what we call mass. Photons do not persist in that way. They are pure motion. When motion reorganizes into something that can rest, mass appears. This is why saying that mass is trapped light is not quite right, but not completely wrong either. More accurately, mass is trapped energy, and photons are one-way energy travels. In the early universe, this interchangeability dominated everything. Shortly after the Big Bang, temperatures were so high that photons constantly converted into particle pairs, and particle pairs constantly annihilated back into photons. There was no stable matter in the sense we know today. Everything existed in a dynamic balance. As the universe expanded and cooled, energy densities dropped. Photons lost the ability to create massive particles freely. Matter began to survive. The balance shifted. The universe froze in a new phase. This history is written into the radiation we still observe today. Measurements of the cosmic microwave background, supported by missions operated by NASA and ESA, reflect the moment when matter finally gained the upper hand over radiation. Even now, the process continues in extreme environments. High-energy gamma rays striking Earth's atmosphere produce cascades of particle pairs. Around neutron stars and black holes, intense radiation fields generate matter and antimatter in enormous quantities. In particle accelerators, physicists recreate these conditions, deliberately converting energy into mass and back again. The rules never change. Pair production requires a minimum energy. That minimum corresponds exactly to the combined mass of the particles produced. Below that threshold, nothing happens. Above it, the process becomes possible. This reinforces something we have already learned. Frequency determines energy. Only photons with sufficiently high frequency can create matter. Brightness alone is irrelevant. You cannot combine many low-energy photons to create one massive particle unless they interact in a very specific way. Again, nature counts in steps. This also explains why everyday light does not spontaneously turn into matter. Visible photons simply do not carry enough energy individually. No matter how bright the room is, the photons are too gentle to build mass. Some light is strong enough to make things. Most light is not. It means that particles are not the most fundamental entities. Fields are. Particles are stable excitations of those fields. Photons are unstable excitations in the sense that they cannot rest. Under the right conditions, excitations can change form. Matter is not eternal substance. It is organized energy. This view also clarifies why antimatter exists. When photons convert into matter, they must produce particles in pairs with opposite properties to preserve conservation laws. Matter and antimatter are created together. Their later imbalance in the universe is a separate question, one that touches on deep asymmetries in physical laws. The photon sits at the center of this unity. It is the simplest messenger between energy and matter. It carries energy cleanly. It converts cleanly. It obeys the same rules everywhere. Even nuclear reactions, which seem far removed from light, rely on the same principle. When nuclei bind together or break apart, small amounts of mass are converted into energy, often released as photons. The sun shines because mass becomes light in its core. Every ray of sunlight is a reminder that matter and light are not opposites. They are expressions of the same underlying reality. Richard Feynman once emphasized that the equations of physics do not care what we call things. They care only about how quantities transform. In that sense, photons and electrons are different dialects of the same language. This perspective also removes the need for speculation. There is no hidden reservoir where mass is stored separately from energy. There is no special substance that makes matter real and light less real. Both are real. Both are measurable. Both transform into each other under precise conditions. The experiments leave no ambiguity. Photons can become matter. Matter can become photons. Energy flows through these transformations without loss or gain, guided by conservation laws that have never been violated. This is not a philosophical statement. It is a summary of experimental fact. And now, with this unity established, we reach the final pressure point. If photons are not objects but excitations of a field, and if matter itself is another form of organized energy, then asking what a photon is may be asking the wrong kind of question altogether. That realization does not end the story. It sharpens it one last time toward a definition that abandons imagery and keeps only what experiments demand. What if asking what a photon is has always been the wrong question to begin with? After more than a century of careful experiments, failed intuitions, refined theories, and increasingly precise measurements, this question no longer feels provocative. It feels inevitable. Every attempt to describe the photon as a thing, an object, or a tiny carrier moving through space has eventually collapsed under the weight of evidence. And every time physicists returned to the data itself, the same pattern emerged. The photon refuses to behave like something that exists independently of interaction. From the very beginning, the photon entered physics, not as a visible entity, but as a necessity imposed by experiment. It appeared first in blackbody radiation, where energy exchange refused to be continuous. It reappeared in the photoelectric effect, where electrons responded instantly and indivisibly. It challenged intuition again in interference experiments, where single detection events accumulated into wave-like patterns. It carried momentum without mass, moved at a speed set by space-time itself, revealed internal structure through polarization, and transformed seamlessly into matter under the right conditions. Each of these discoveries added a new constraint, and together they quietly removed one option after another. The option that vanished was the idea that a photon is an object in the classical sense. Objects persist. They have trajectories. They occupy positions between interactions. They can be described independently of how they are measured. Photons do none of these things reliably. No experiment has ever observed a photon halfway through an interaction. No measurement has ever tracked a photon's continuous path without disturbing the very conditions required to observe it. No definition of where the photon is between emission and absorption survives experimental scrutiny. What does survive is something more precise and more powerful. The photon emerges as a rule. It is a rule governing how electromagnetic energy is exchanged. It specifies how much energy can be transferred in a single interaction. It specifies how momentum accompanies that transfer. It specifies how probabilities evolve between interactions. It specifies how detectors respond, how atoms absorb and emit, how fields adjust, and how space-time constrains motion. In this sense, the photon is not a building block of reality in the way stones build a wall. It is a constraint that reality obeys. This is why quantum field theory describes photons as excitations of a field rather than as particles moving through empty space. The electromagnetic field exists everywhere. It has allowed states and forbidden ones. When the field changes state by the smallest permitted amount, we call that change a photon. Nothing more is required. This view dissolves many long-standing confusions. It explains why photons can be created and destroyed without violating conservation laws. It explains why photon number is not fixed, while energy accounting remains exact. It explains why photons cannot be localized the way massive particles can. It explains why asking about a photon's internal structure leads nowhere, while asking how it interacts leads to precise predictions. Even the language of wave-particle duality begins to look outdated from this perspective. There are no waves turning into particles or particles pretending to be waves. There is one mathematical structure producing different observable behaviors under different conditions. When interactions are frequent and numerous, the field behaves smoothly and classical waves emerge. When interactions are rare and discrete, individual events dominate and photons must be counted. Both descriptions are approximations of the same underlying rule set. This is not philosophical restraint. It is experimental discipline. Every major advance in understanding light has come from letting experiments decide which questions are meaningful. And repeatedly, the experiments have pointed away from imagery and toward interaction. This is why the most careful physicists have always warned against over-interpreting mental pictures. Richard Feynman expressed this with characteristic clarity when he said, "Do not keep saying to yourself, if you can possibly avoid it, but how can it be like that?" He was not discouraging curiosity. He was discouraging attachment to intuitions that experiments have already outgrown. The photon teaches this lesson gently but firmly. When we ask what a photon is, we are tempted to imagine a tiny thing flying through space. When we ask how a photon behaves, the data answers cleanly. Energy is exchanged in fixed amounts. Momentum accompanies energy. Probabilities interfere. Speed is invariant. Polarization encodes structure. Matter and light transform into each other. None of these statements require a picture of a moving object. All of them require precise rules. This approach also explains why photons feel elusive. Rules are not things you can point to. They are constraints you infer from consistency. The photon is visible only when it acts. Between actions, it does not announce itself. This does not make photons less real. It makes them more fundamental. In modern physics, reality is not built from solid pieces alone. It is built from relationships, symmetries, and limits. The photon sits at the intersection of all three. It expresses the symmetry of the electromagnetic field, the relationship between energy and momentum, and the ultimate limit on how information travels. This is why photons appear everywhere in our understanding of the universe. They carry signals across billions of light years. They encode the composition of stars and galaxies. They shape the evolution of the early cosmos. They regulate chemistry, biology, and perception itself. And yet, despite this central role, they never reveal themselves as tiny objects drifting through space. Light does things. When it does them, we can see it. When it is not doing anything, there is nothing to see. The rules tell us what light can do. After a century of refinement, no deeper object-based description has replaced the interaction-based one. Every new experiment has strengthened it. Organizations such as NASA and ESA rely on this understanding every day. Instruments aboard the James Webb Space Telescope do not ask what a photon looks like. They count interactions. They measure frequencies. They record polarizations. They infer structure from rules obeyed with extraordinary precision. The universe responds accordingly. This does not mean that curiosity ends here. It means that it has been guided to the right place. Instead of asking what photons are, physics asks what rules govern energy, exchange what symmetries constrain fields, and what limits space-time enforces. Those questions continue to lead somewhere. As this journey closes, the picture that remains is coherent, restrained, and experimentally grounded. Light is not mysterious because it hides its nature. It is precise because it follows rules without exception. If this series has shown anything clearly, it is that the photon is not an object waiting to be imagined correctly. It is a boundary condition the universe never violates. Thank you for staying with me through this long journey tonight. If these ideas brought you even a small sense of calm or understanding, a gentle like or a soft tap on subscribe is a quiet encouragement that helps me keep creating these night stories. And if you feel like it, I would love to know where you are listening from or any thoughts you'd like to share. May the rest of your night unfold peacefully, and sleep come easily. Good night.